Hi students, welcome to part 3 of thermodynamics. This is chemistry chapter 14 and today's topic is entropy. Entropy is defined as just disorder or randomness. So if you see that cartoon on the top of the worksheet, you should have printed it off. The definition of entropy is a measure of the disorder that exists in a system. So it's the amount of energy in a system that is not available to do work. So energy, you remember, is the ability to do work. So entropy is a measure of how much energy that might be in a system, but is not available to do work. The greater the amount of disorder in a system, the greater the entropy. So the first law of thermodynamics states that energy cannot be created or destroyed. The second law of thermodynamics says that the entropy in the universe must always either increase or remain the same. It can never decrease. So that's important when it comes to overall in the universe, entropy cannot decrease. But in individual reactions, you can see a decrease in entropy. We'll see some of that later on. So that little diagram you have there shows the difference between solids, liquids, and gas. As you go from a solid to a liquid, you are increasing entropy. The molecules are less organized, they're more random. And as you go from a liquid to a gas, it becomes even more so. The reverse is true. As you go from a gas to a liquid, the entropy is decreasing, and from a liquid to a solid, it's even decreasing anymore. Another thing that greatly affects entropy is temperature. So the higher the temperature, the greater the molecules are moving and the more entropy you have. So we use delta S to stand for the change in entropy. So entropy is abbreviated with an S. Remember, enthalpy is abbreviated with H. Delta S stands for the change in entropy. So if a system gains entropy, its delta S is going to be greater than 0. If it loses entropy, its delta S is going to be less than 0. So there's some things that we can look at to determine the sign of entropy. So what we're going to do, we're going to first get some practice looking at how the entropy changes, the sign, whether it's increasing or decreasing. And then the second part, we're going to talk about how to actually calculate values for entropy. But to understand just from a qualitative standpoint how entropy changes, the phase is the most important thing. So if you have a chemical reaction and you have a solid going to a liquid, then it's going to be increasing entropy because a liquid is more random and disorganized than a solid. But if all of the phases in your chemical reaction are the same, then what we do is we count the number of molecules involved. The more molecules involved, everything else being equal, the more randomness there is. And so going on to look at these other parts on your worksheet. In general, the side of the reaction with the most molecules in the gas phase has the highest entropy. If no gases are present, then the side with the most molecules in the liquid phase has the most entropy. And if everything is a solid, the side with the most molecules has the highest energy. Okay, so we've got 4 chemical reactions there. And if we look at the first one, carbon dioxide, solid, going to carbon dioxide, gas. We know that gases have more entropy than solids. So for that first one, the delta S is greater than 0 because what is happening is the entropy is greater than 0. It's increasing. So that would be how you would do number 1. Number 2, if you look at the phases, everything is a gas. We've got 1 nitrogen gas and 3 hydrogen gas molecules on the reactant side, and 2 ammonia molecules on the right side. The number of molecules has decreased. Even though they're all gases, the number of molecules has decreased. So it's lost entropy. So in this case, delta S is less than 0. That would be for number 2. Number 3, we have water, a molecule of water going from a gas to a liquid. So it is actually losing entropy because a liquid has less entropy than a gas. And the 4th one, those are all solids, so you just count the number of molecules. There are 5 molecules on the left side and 2 on the right. So it is decreasing in entropy as it goes through the reaction. Okay. Now, turn your worksheet over. So for this part here, you need to make sure that you have your calculator handy. We are going to be using the calculator here. So remember, with enthalpy, we learned 3 ways to calculate enthalpy. Make sure you know these 3 ways. They will be on the test. The first way was by just doing an experiment and calculating enthalpy. The second way was bond energies, where we counted up all of the different bonds and how much energy was in each bond and how much energy was required to break the bonds and reform the bonds. The third way was using Hess's law. So for calculating delta S, the change in enthalpy is going to be very similar to Hess's law, where we add up all of the entropy from the products minus the entropy of the reactants. And the table for that can be found in your textbook, and it can also be found on the bottom of the inside back cover, the table that says absolute entropies. So we are going to talk a little bit about that before we actually do a problem. Some things to notice as you look at that table. First of all, the units are joules per mole times Kelvin. So it's not kilojoules. This amount of energy, we're going to use joules because generally they're smaller numbers. We also include K for Kelvin in the equation. So we'll see why that's important in the next section that I'm going to be talking about. Remember the S with a little degree sign to the right, it's a superscript. That means that the entropy is at standard temperature of 25 degrees. Since entropy changes with temperature, these values in the book are only valid at standard temperature. Also, since an entropy can never be 0, it's always going to be a positive number. You're not going to see any negative values for the entropy. And also notice that even though elements don't have enthalpies of formation, they do have absolute entropies. So these problems are going to be very, very similar to the Hess's law you just did. The only thing changing is the units. So let's go through and do a problem. So we want to know, what is the delta S for the complete combustion of methane gas? So we've done methane gas equations in this whole chapter. So we're going to do it again. So if you remember the equation for the complete combustion of methane, go ahead and write that now. You might want to pause the video and write that, and then you can restart the video. Remember, phases are important. Okay, so this is, let's figure out how to get this. This is the equation. So what I'm going to do now is go through, and I'm just going to write underneath each molecule, I'm going to write what its absolute entropy is from the table. So CH4, methane, is a gas. If I look in the table, I see that it has 181.6, and that's joules per mole times Kelvin. Okay, now I'm looking at O2, oxygen. Oxygen, according to the table, is 205. joules per mole times Kelvin. Carbon dioxide, gas, (213.7 joules per mole times Kelvin. And water, if you look at water, there's different absolute entropies for water depending upon if it's a gas or a liquid. In this case, it's a gas. Okay, 188.7. I'm not writing the units in for all these just because of space. So let's go through now and use similar to Hess's law. We're going to add up the total of the products minus the reactants. So delta S equals 1 mole of CO2 times 205. The moles are going to cancel here. Two moles of water minus 1 mole of methane plus 2 moles of oxygen. Apologize if you can't see that in very well. Okay, we're going to add those together. We'll get 591 joules per Kelvin on the product side. This is a minus sign, minus 596.1 joules per Kelvin. Subtract those, you're going to get a negative 5 joules per Kelvin. So that's how you do calculate absolute entropies using the table. Okay, I'm not going to go through another one of these problems because we should have had a lot of experience doing those with the enthalpies. This is very kind of similar kind of reactions, similar kind of equations. So the next topic we're going to talk about is Gibbs free energy. So Gibbs free energy is abbreviated G, so that's good. Easy to remember that one. So what Gibbs free energy is, it relates the change in enthalpy, the change in entropy, and temperature to determine if a reaction can occur spontaneously or not. So for a reaction to occur spontaneously, the sign of delta G must be negative. If delta G is positive, the reaction cannot proceed on its own because it violates the second law of thermodynamics. So it doesn't mean, so reactions obviously don't all just start on their own. For example, you have to have activation energy to start chemical reactions. Think about starting a fire. You have to strike a match and increase that activation energy. But once that reaction begins, it's spontaneous. It's going to go on its own. So that's what it means. It doesn't mean it doesn't have activation energy. It just means that once it starts occurring, it will occur spontaneously. There is an equation to calculate Gibbs free energy, and it combines, delta G stands for Gibbs free energy, and it uses the change in enthalpy minus temperature times the change in entropy. So the equation looks kind of confusing at first, but I want you to think about this using what you learned in algebra about adding and multiplying with signs. Let's do a couple of really simple samples here. So just to remind you, if the delta G is negative, the reaction will occur spontaneously. Also, another way you can think of Gibbs free energy, you can think of it, instead of the word free, it might make more sense if you think Gibbs available energy. Okay, let's just say that I'm going to put random simple numbers in here. Let's say my delta H is 10, my temperature is 2, And this is Kelvin, by the way. Temperature's got to be in Kelvin. And my delta S is 2. What would my delta G be there? If I plug those in, just think of those as like X, Y, and Z variables in an algebraic equation. You would have 10 minus 2 times 2 is 4, and that would be 6. So that reaction would not be spontaneous because the Gibbs free energy is a positive number. But let's say we change this, and let's say our change in enthalpy is still 10, but now let's say our temperature is 20, and our delta S is still 2. So that would change it. We've increased the temperature. When you increase temperature, you're increasing the entropy. So in this case, we have 10 minus 40 equals minus 30. That's a negative number. That reaction would be spontaneous. Okay, so what we are going to do is we are going to calculate some couple of problems where we're given delta H, we're given delta S, and we're given temperature. There might be problems when you're not given delta H and you have to calculate delta H first, but in these first two problems, we don't need to worry about that. Okay. Determine the value of G and state whether the reaction is spontaneous if delta H is minus 32 kilojoules, delta S is 25 kilojoules per Kelvin, and temperature is 293 Kelvin. Okay, we're going to use that simple equation that we just did. Delta G equals delta H minus T delta S. Okay. I'm just going to put those numbers in. I'm going to write it down here. Make sure you use your signs on these problems. Okay, that is how you would set the problem up. I'm going through it, write each step down for you, here for you. Kelvin cancels out. So we have negative 32 minus 7325. Those are both negative numbers. We'll end up with minus 7,293 kilojoules. That's a negative number. So yes, that is a spontaneous reaction. Okay, number 7. Number 7, we're going to do it the same way. It tells us that delta H is 12 kilojoules. Temperature 290 Kelvin. Delta S, negative 5 kilojoules per Kelvin. Okay, in this case, we have 12 kilojoules minus, okay, look what happens here. This is a minus. This is a minus. We multiply a negative sign by a negative sign. We get a positive sign. So this is going to be plus 1450 kilojoules. The delta G in this one is 1462 kilojoules. That is not a spontaneous reaction. See how the signs are so important? So make sure you include those as you're going through, and just think about your rules for multiplying and adding signs. So you can see you can't just look at the data and automatically know whether it's spontaneous until you work it out in an equation. Okay. Turn the page. So, all right. So just as in Hess's law and in entropy, the standard absolute entropies, we have a way to use a table to calculate the whether a reaction can proceed on its own or not. So in the inside back cover, this equation, this table up here, has to do with Gibbs free energies of formation. So we can use those tables to calculate delta G. Now in this case, we don't need delta H, we don't need delta S. We can calculate directly from the table, just like Hess's law. A couple things to remember though is the Gibbs free energy of formation of an element in its elemental phase is 0. So once again, it's 0. Also, there's some things are positive and some are negative here. So, and I wrote the equation a little differently. Remember that little circle means under standard conditions. And I just use the summation sign, which you guys probably might have learned in math or might not. That just means the sum of, I'm just writing it differently. It's the same idea. The Gibbs free energy of formation under standard condition of the products minus the sum of those for reactants. Same thing, just written, just different notation in the way I wrote it. Okay, we're going to use that information to calculate what is the Gibbs free energy of this reaction. So this is the reaction C6H6. That's actually benzene. You might have heard of benzene. It's used in producing a lot of industrial uses and adhesives and things like that. You might recognize this as, what kind of reaction is this? If you said a complete combustion, you would be correct. Okay, we need to know the phases. This is a liquid. Oxygen is a gas. These are gases. Okay, I'm just going to write the standard Gibbs free energies of formation above them so you can see that. Looking at the table, C6H6, the table has it both in the gas form and liquid. This is the liquid form, so it's 124.4. I didn't talk about the units, but these are kilojoules per mole again. Okay, kilojoules per mole. Okay, oxygen, this is in its natural phase. Oxygen gas is the natural phase of oxygen, so it's going to be 0. Carbon dioxide gas, according to the table, is minus 394.4, and water in the gas form, minus 228.6 kilojoules per mole. Okay, I'm going to sum up my products. 12, that coefficient's 12. Remember that stands for 12 moles. Kilojoules per mole, the moles are going to cancel. Plus, this is another negative. And I'm running out of room. Minus, those are my products, minus my reactants. And for oxygen, it's 0. Okay, so I'm going to add those up, multiply that out, and add them up. Minus 6140 kilojoules. Okay, now I'm going to add those up, minus Okay, those are both negative numbers. Adding two negative numbers together. And that is my Gibbs free energy. The fact that it is a negative number tells me that, yes, it is spontaneous. Okay, so that's two different ways to calculate. You can use the table if you know the conditions, or you can use the other one if it's not standard conditions, but you know temperature and you know delta H and things like that. Okay, we're going to do one more. This last one is like using the equation. We're going to be given some of the information, and we just need to figure out in this reaction, if a reaction has a delta H of minus 120 kilojoules per mole and is spontaneous for all temperatures less than 200 K, what is this delta S? This is also important to be able to use your algebra signs correctly. So we know we want delta G needs to be less than 0 for it to be spontaneous. So we're going to treat this reaction, we're going to say delta H minus T delta S has to be less than 0. So I'm going to put those numbers in. Delta S is my unknown. So if I add this to both sides and then add it to that side, I'm getting rid of that, so then I end up with minus 200 K, delta S is less than 1200 kilojoules per mole. Now I'm going to divide both sides by 200 to get this by itself. But you remember from algebra, when you divide by a negative number, you flip the sign of an inequality. So if I divide this by 200 and this by 200, what I end up with is delta S is greater than 0.6 kilojoules per mole times Kelvin. Divide by a negative number, you flip the sign. So this is telling me that for this reaction to be spontaneous, delta S needs to be greater than 0.6. Okay, and that is the rest of that chapter. At the bottom of your worksheet, I have put a couple of really good websites. If you're still having trouble with this whole idea of entropy and Gibbs free energy, you can visit that website. Or there's tons of other good websites if you still want more information. So have a good week.